Hello everybody, and welcome back to another video on my channel. Today we will be talking about a very important concept and a logical extension of the last video. Now let's move on to the video. In our last video I talked about angular kinematics, basically angular displacement, velocity, and acceleration. But the thing is, that's just part of the story. The other part is force and momentum and all of that. And this is the first step in doing that. I'm going to be talking about torque, which is essentially the rotational counterpart to force. So, let's move on to actually explaining what torque is. Now, the actual definition of torque, and torque is written like this, sort of like a lowercase t, but instead, not lowercase t, sign of like a mini uppercase T with like a hook almost, like a hook and then a line on top of it. This is the cross product of the force vector and the displacement vector. So this means that torque is also a vector. And by these units, the units of this are Newton meter. Now you might be like, wait, isn't this a joule? But no, this is not a joule. This is specifically a Newton meter. So that's why when we talk about joules and energy versus this, they are two different things. Because if you remember, energy was the dot product versus the cross product. So those are two different things. Now, the magnitude of torque is equal to the magnitude of the force times the magnitude of the displacement vector times the sine of the angle between them. Now, basically what this means, that means if I push in the same direction as the object, like as the displacement, that means I'm just going to push it translationally, and that's just regular force with no torque involved. But besides that, the other thing is if I took directly perpendicular, I will get the maximum amount of torque. But if you notice, about work, since it's a dot product, that means I will have no work done. Since I'm not actually moving it, I'm just making it rotate around its center of mass. Speaking of center of mass, that is something we're going to talk about in a video in the near future. So, now that all of that is explained, let's draw a diagram to explain how this works so you understand it better. So, torque essentially acts like kind of like a lever. And for this, we're going to say we have a hinge over here. Now, let's draw a rod like this. And let's say we apply the force over here. So the distance from the application of force to the hinge is the distance r. And let's say we apply the force like this. Now, if you notice, this angle with the horizontal in green is the theta in our equation. This maps to this, and this maps to this, and then of course you just have the force that you're applying to create the torque. Now, this is just a one-sided hinge. There are also other applications. Let's say we also can have like a seesaw, or what's called in physics also a first-class lever, and instead this is the center point. So if it was here, this wouldn't be the distance, and this wouldn't be the distance. Instead, what would be the distance? It would be between here and the center. And this would, if we had a weight on here, this weight would go straight down or perpendicular to, so the torque would just be the force applied on this, and many problems will ask you to balance this lever. So you'll have to balance the torques, not the force. But that's something more relating to static equilibrium. So I think that's really about it for introduction to torque. I'm going to keep these intro videos relatively short, so when I explain more things, I can actually show you problems where it's actually going to be used instead of just something very basic that you're probably not actually going to use. So, thank you so much for watching this video. See you in the next one, and bye-bye.